Hello and welcome everyone. In this lecture, I am going to derive the OLS estimators in deviation form. Before beginning the derivation, let me share an important point about regression lines. In regression lines, we generally use subscripts with variables, while constants do not require any subscript. In our regression line, y, x and the error term are variables that will have subscripts. The subscripts we typically use are I for cross-sectional and T for time series data. Let's assume that the data we are using is cross-sectional, so we are using the first equation for derivation. Remember one thing, in the equation of regression line, the first two terms constitute the predicted value. That is, if we know the value of beta naught and beta 1, we can predict the value of y. For example, in our previous lecture, we estimated the value of beta naught and beta 1, and the regression line was, if we want to predict the value of y at x equals to 4, we will put x equals to 4 in equation 2. So this is our predicted value, and to show that it's a predicted value, we put hat over y. So y is the actual value and y hat is the predicted value. So in equation 1, beta naught plus beta 1 x gives us the predicted value of y. So we can write equation 1 as y equals to y hat plus error term. In simple word, the actual y value is equals to the predicted value of y plus the error term, where y hat is equals to beta naught plus beta 1 xi. Now using the third equation, we can find the value of beta naught. To isolate beta naught, we can move beta 1 x to other side of the equation and we get equation 4. However, this approach would yield multiple values of beta naught. For example, if we have 4 observations on y and x like we were having in our previous example, by substituting each pair of x and y values one by one into this equation 3, equation 4a, we would get 4 distinct values of beta naught. Similarly, if your sample size is 10, you would end up with 10 distinct values of beta naught. Nevertheless, I previously mentioned that both beta naught and beta 1 should have single values. These are constants. To resolve this, we apply summation on both sides of the equation 4. By summing y values, we obtain a single value for y, and the same holds true for the x values. So summation allows us to arrive at a single unique value for beta naught. Thus we have the following equation. Since we are interested in finding the value of beta naught, we must have just beta naught on left hand side of equation 5. For that, we need to divide both sides of the equation by n. On left hand side, the n in the numerator and the denominator will be cancelled out, while on right hand side, summation y over n would give us mean of y, and summation x over n would give us mean of x. So here we have got the value of beta naught. Now we are going to derive the formula of beta 1. If you recall from the previous lecture, the goal of OLS approach is to minimize sum of squared residuals. And we know that error is the difference between actual value and the predicted value of y, and y hat is equals to beta naught plus beta 1 xi. Putting 3 into 2, we have equation 4, and putting equation 4 into 1, we get equation A. As we have already derived the formula of beta naught in this lecture, now I'm going to substitute the value of beta naught in equation A. We can rewrite this equation as, from the last two terms we can take beta 1 common, and I have written the y values and x values in brackets. This is our equation B now, which is equals to sum of squared residuals. Now to minimize sum of squared residuals, we have to apply first order condition, where we would take derivative of equation B with respect to beta 1 and set the resulting derivative equals to 0. Apply the power function rule of the derivatives here. Bring the power into the base, write the function and subtract 1 from the power, and then take the derivative of the function without power and set the resulting derivative equals to 0. Here you can see that the first term doesn't have beta 1, so its derivative with respect to beta 1 would be 0, while in the second term we have beta 1, so derivative of beta 1 with respect to beta 1 will be 1, and we are left with minus xi minus x bar. Now take minus 2 to another side of equality, and 0 divided by minus 2 would be 0 on right hand side. So we are left with the following equation. Now in this equation, multiply x minus x bar with the terms inside the bracket, and then apply summation, and we get the following equation. As our main goal is to find the value of beta 1, we need to isolate beta 1, and to do this, take this term to another side of equality, and we get, now divide both sides of this equation by summation xi minus x bar whole square to have just beta 1 on one side of equality, and thus we get the following formula for beta 1. This is the alternate formula of beta 1 in deviation form, and to simplify it we can express it as follows. Here I have used small letters small x and small y, where small x the deviation of x values from its mean value, and small y represents the deviation of y value from its mean value. So throughout this course, we would be using capital X and capital Y for raw form of the data, whereas small x and small y for the deviation form of the data, where we are subtracting mean values from the actual observations. Now we are going to use the formulas that we have just derived on the same sample that we used in our previous lecture. The sample we used in the previous lecture was as follows, and to apply the formula of beta naught and beta 1 in deviation form, I am going to find small x and small y, which are the deviation form of x and y respectively. To find the deviation form, we need to calculate the mean value of x and y first. The formula of mean value of y is summation y over n, and for x is summation x over n. Here summation y is equals to 18 and summation x is 24. To find the deviation form, you need to subtract the mean value of y from each of the y observation. For example, in our case, mean value of y is 4.5 and mean value of x is 6. To find small y, subtract 4.5 from each of the y observation. Similarly, we will subtract 6, which is the mean value of x, from each of x observations, and we get the following values. Now in the formula you can see that we need to find sum of x into y. That means we need to have a column where we have to multiply small x values with small y values. After multiplication we get the following values, and sum of this column is 17. And in the formula of beta 1, we have summation xi square in the denominator, so we need another column for x square, and the sum of squared values of small x is 14. Now we are going to put the value of summation xy and summation x square into the formula of beta 1. It doesn't matter you write summation xy or summation yx. So here we have summation yx equals to 17 and summation x square equals to 14, and the value of beta 1 is 1.214. Now to find the value of beta naught, we will put the value of beta 1 and the mean value of x and y into the formula of beta naught. Here mean value of y is 4.5, the estimated value of beta 1 is 1.214, and the mean value of x is 6, and the value of beta naught is minus 2.785. You can observe that by using the formula for the deviation form, we obtain the same values for beta naught and beta 1, just as we did in our previous example, where we utilized the raw form of formula for beta naught and beta 1.